All right. So we finished last two lectures, um, actually three lectures, but two topics, right? There we discussed the field of robotics, different application domains, and a bit of history. And then we looked at um, robotics industry, where robots are used in manufacturing processes. And also we looked at the how this technology is connected to the development of the world, right? uh, how the world is moving forward with this technology, and how different industries are using this technology, and how this technology is going to benefit various countries in their development process. So as I always say, when you study technology, you can't take that single out and without any connection to the rest. Some people try to do that. They want to study just that technology, and then they are kind of disconnected from the world, right? So, so what I suggest you do is that um, before you study the technology in depth, right, or else together with your studies, right, of a certain technology, make sure you also look at how it affects the world. What is the future of the world with this technology? How the technology is connected to the markets, to the societies, etc. Then only you can actually talk about this technology to a wider forum, right? That's only when you can actually confidently speak about the technology to someone else, right? So that is very, very important. So it's now that we actually try to get into the technology a bit seriously. Lecture 4 actually, this because we took more than what I usually take, right, for the first couple of lectures. So this time, our topic now is rotation and translation. So I'm going to use some of the slides I borrowed from Professor Khatib at Stanford, and some of the slides I developed myself, I modified, and I use it for teaching purposes. So I want to acknowledge Professor Khatib at Stanford. Uh, so this is one perspective of robotics. What you see there? You see a robot manipulator, obviously, and it is actually holding a very familiar device, an iron, electric iron, okay? And there is a iron board and a t-shirt on that, and the robot is doing ironing, right? That is what you see. And on beyond that, you see that the manipulator is on something. In fact, even though it is not very clear, it is a mobile robot. The black one here is a mobile platform, right? Uh, this one is a mobile platform. It's a different mobile robot, right? And this particular robot, the arm manipulator, is mounted on top of this robot, so that the arm gets the mobility. So let's say the arm has 6 degrees of freedom, and then this robot mobile platform has, let's say, another 3 degrees of freedom, left, right, and rotation. Altogether, it's a 9-degree of freedom system. 9-degree of freedom system. So with the 9-degree of freedom, you can do quite a lot. Okay. So that is one description of what you see, right? Second thing is the first bullet, actually. Manipulator position and orientation should be described mathematically. So this is the physical world that you see, but as engineers, you are working in the back end, okay, behind the scene, right? You don't go to the forefront. In the back end, you calculate the manipulator position and orientation. Say, for example, this point. You can't have the iron here and there, right? You have to put the iron right on the t-shirt, right? Not only one point, you have to move it so that you iron the whole piece of cloth. And also orientation. You can't just put iron like handle down or handle on a side way. You have to put it vertically on top of the piece of cloth, right? So the orientation matters. Orientation matters. Position matters. So does orientation. So now you get into the problem. Whenever you use a robot manipulator, what you are using it for, right? You have to be very serious about. And almost always it's about the endpoint. There is a tool over here, and you have to control the tool in terms of position and orientation. Okay. So you have to find out a way out. How do I calculate the position and orientation of the endpoint, end effector? There are various ways to do that. For example, if you know the angles and the distance lengths of the manipulator, using trigonometry and geometry, you can calculate the position, right? I'm sure you can do that with few equations. You can do that. So there are other ways. So you can read you can have vision systems and then process the images and then calibrate them and then figure out where the endpoint is. There are various ways to do it, right? So, however, it's important that you know the position and orientation of the endpoint. Number two, the second word, all the parts of the manipulator, including the end effector and the links and other surrounding objects. There are tables, chairs, etc. around the manipulator. You need to know about these things. Also to be described using mathematical relationship. So you need to have some sort of mathematical framework to describe all these things, just like in a physical environment, your living area, at your houses, dining area, there are objects around. So there we don't think about mathematical description. But here, you have to represent everything mathematically. So how do I represent a chair mathematically? How do you represent a mobile platform mathematically? How do you describe anything else, let's say iron board, right? A sofa, a table, whatever, mathematically. You need to describe everything mathematically, right? You have to figure it out, how to do that. Then only you can combine all these things as a one environment, right? Okay. And some objects are moving, like for example, chairs and tables are not moving, right? But the manipulator links, and if there are people, you have to represent them also mathematically, right? They're moving, so you have to update their position. Okay. Again, you can use vision systems and figure out where the objects are, and then create your environment. But there are other ways also. Okay. So joint actuators are controlled according to the spatial position and orientation of the manipulator, right? So now let's look at the manipulator alone, right? So these are the joints of the manipulator, here, here, and one over here, and a couple of joints here, right? They're all actuated joints, which means every joint has an actuator, right? The actuators are controlled. These are motors, basically servo motors, right? And there are encoders to read their position according to the spatial position and orientation of the manipulator, right? Right. Now let's look at the problem I just mentioned. How do I represent the objects in my workspace mathematically, right? So the answer is simple, right? Not as difficult as you might have thought, right? We use what is called body frames. Body frames. These are coordinate frames. If you look at this illustration here, You can see the manipulator, you can see some objects, the base of the manipulator, cubic something over here, the cylinder, right? So I assign coordinate frames to each and every object that I want to mathematically describe in the environment, right? So when I place a coordinate frame, XYZ Cartesian coordinate frame to this object, I specify this point where I have the laser pointer now. This is the position of the object. And this is the orientation of the object, x-axis, y-axis, z-axis. Let's say z is our, let's say, if you want to represent a human being, z is basically the body line, okay, the vertical line. That is z. Then if you stretch your arm sideways, right, that can be your y-axis. And then in front of you, right, from your chest outward is your x. All right. So your x coordinate axis is the axis which is normal to your body and coming out of your chest, vertically outward. That is your x direction. So when you walk forward, you are walking along your x-axis. And if you have your left hand, right, lifted to 90 degrees from your body, and that is your y-axis. Okay. So now the other way around. So x is forward, z is upward, right? And then, yeah, sure, y-axis is to the left, fine. So because it has to be right-hand coordinate frame. So similarly, all the other objects here, the cylinder has an axis. Usually we give z axis to the major symmetrical axis of an object. So you can see like that, the base, all the other joints, even the end effector, you can see the effector here. It's a gripper here. And there you can have, in fact, in this particular case also, x is forward, right? X is forward. Y is like this, Z is like that. So I actually do not agree with this one. I would rather have Z axis to the front like this. You see, because it is the front axis here, like major axis of the gripper, you said. But if you want to have your motion along your major axis, this is good. This is correct, right? So, but it doesn't matter mathematically. If you want to have a physical consistency in assigning coordinate frames to the objects, you might have a problem, right? Assigning coordinate frames to different objects, a human being, a gripper, another object. Where do I put my Z, my X? Different people come up with different rationale about assigning this access, right? Mathematically, it doesn't really matter. Okay, it's just a physical choice, right? So once you place coordinate frames like that, you need to relate the coordinate frames to each other, right? The cylinder with respect to the frame, a gripper, right? The gripper with respect to the base, like that, right? So there are mathematical descriptions how to relate different coordinate frames. Okay. Say for example, now you see here 4 coordinate frames. But as you understand, there should be one universal frame, right? Like world coordinate frame, to which every other frame is referred to, right? So in that aspect, you will see one of these frames has to be the world coordinate frame, the absolute reference, right? Maybe I would pick up this one if I have a choice as my world coordinate frame. The base of the manipulator, I would choose as my world coordinate frame, and all the other frames are described with respect to this frame, the world coordinate frame. So these objects are actually relative objects to the base of the manipulator. Even the gripper of the manipulator is relative to the base of the manipulator. So then it makes a lot of sense, right? So now the problem is how I define, okay, how can I find the relationship between these two coordinate frames, or else in a different way, how can I describe the end effector, right, position and orientation with respect to the base coordinate frame. Okay, like that. So this is what we are going to do today. So with that understanding, if I just generalize the problem at hand, right, when it comes to a manipulator, right, this is what Professor Khatib has drawn to describe the manipulator to his students. You have the base, right, you have the links, base and the links. And at the end, you have the end effector, right? This is a serial manipulator. So between any two adjacent links, there's a joint. Some joints are revolute joints, which means the following link rotates with respect to the preceding link, right? The following or successive link is rotating relative to the preceding link. But sometimes there are prismatic joints, right? Not very popular, but you can have a prismatic joint as well. In that case, the successive link is moving linearly, right, with respect to the preceding link. So that is the prismatic joint. Okay. So links and joints, right? These are the main ingredients of a manipulator, links and joints, right? So if you have n moving links, right, then one fixed links. So the one fixed link is the base actually. And then you have n moving links, link 1, link 2, link 3, link 4, like that. That is how we define or number links. Then the joints, revolute or prismatic. So usually every joint has 1 degree of freedom. But sometimes there are some complicated joints that contribute to more than 1 degree of freedom. Okay. Now, the operational point is very, very important, right? Operational point is actually the end effector position of the robot arm, right? So let's say there's a robot arm, it goes like that. This is the end point. You can see some of the parts of the manipulator at the end of the arm. And look at this point where I have my laser pointer right now. So if this manipulator grips something, or if it is performing a certain duty, task, right, it's actually performing around this point. And it is what is called the operational point, or n+1. Okay. Why I say n+1? It is because this is going to be another coordinate frame. As you can see over here, the red 3 arrows, right? They generate another coordinate frame, which is not actually part of the robot manipulator. This is where the operation is going to happen. So you define another coordinate frame. So please understand that you are free to assign coordinate frames at will, right? If you see there's a need to assign a coordinate frame to a certain object, you have to do that. So then you will increase the number of coordinate frames you are handling in your workspace. Okay, so there you can see joint n, right? And then this is link n, joint n, link n. So after that, there is no joint at this point, but there's a link. So there's actually no link, but it is a virtual frame, right, to describe this point, operational point. All the other coordinate frames are attached to links. Okay. So if you have n number of links, there are n number of coordinate frames. But at the end of the arm, right, there is this point, and you call it operational point, and you assign a new coordinate frame. Right. Then let's look at the other things. Simple M, number of independent variables required to describe the position and orientation of the end effector. Right. Number of independent variables. So if you want to describe the end point, right, the position and orientation, how many independent variables do you need for that? So in 3D space, if you look at 3D space, m equals 6. Obviously, you need 3 variables to specify x, y, z, and 3 more for direction. Altogether 6. But sometimes you don't operate your machine, your manipulator in 3D space. Sometimes it's just 2D space. Okay. Like what? XY table. So there you don't have any Z movement, right? You don't have to control that. So then you are in 2D space. You can also be in 1D space as well. Then it becomes very, very simple manipulator. You sometimes don't call it a manipulator, right? Just a lead screw. Now, so simple M is the number of independent joint variables, number of variables that you need to specify position and orientation. Okay. And if you have a manipulator which has n number of degrees of freedom, so n is the number of degrees of freedom in your manipulator, m is the number of independent variables you need to specify your position and orientation. Okay. Now, for instance, let's say n is greater than m, which means you have more degrees of freedom in your manipulator than the number of variables you need to arbitrarily specify orientation and position in your space, workspace. Then the manipulator you have is a redundant manipulator. Okay. So if you are in a 2D space, right, m is 2, but if you want to have orientation, you can add that one, then it becomes 3. So if you have manipulator more than 3 degrees of freedom, it's a redundant manipulator. In 3-dimensional space, if you want to describe your position and orientation, you need to have 6 degrees of freedom. Let's say you have a manipulator with 7 degrees of freedom, which means n is greater than m. So what you have is a redundant manipulator. And the degrees of redundancy, actually, degree of redundancy is n minus m. You can calculate that. So if you pay attention to the second bullet over here, if a manipulator has more than 6 degrees of freedom, there exist an infinite number of solutions to the kinematic equation. So this kinematic equation means equations that you write, right, using the position, velocity, acceleration, right? We call kinematic equations. And in this case, you can just say position only, right? These are kinematic equations, but there is another type of equations we call dynamic equations. There you have time, forces, torques connected with acceleration, inertia, etc. Then it becomes a dynamic system. Okay. Here it's only just mathematical or kinematic description. We talked about the human arm last week. Human arm has 7 degrees of freedom. The shoulder, 3 degrees of freedom is a spherical joint, right? Spherical joints, they have 3 degrees of freedom. And then the elbow joint, 2, and the wrist, 2. Okay, 3, 2, 2 is 7. If you want to handle any objects around you, right, you have to control your hand position and orientation. Okay, you can do it very, very easily because it's a redundant manipulator, redundant arm, because 7 is more than what you minimally need, which is 6. Okay. Right. Now we are going a bit into mathematics. First of all, we will figure out the spaces we are dealing with, right? We are dealing in. So this is the manipulator again, the base of the manipulator, right? The first joint over here, first link, second joint, second link, third joint, third link. That's it. Link 1, link 2, link 3, joint 1, joint 2, joint 3. Okay. There is no joint over here. And this is the operational point. There is no joint there. So you can have your first coordinate frame over here, second coordinate frame over here, third coordinate frame over here. And there's no coordinate frame over here, but you can assign one for your operational point. Okay, that's what I said. This is n plus 1. N is 3, and this is 4th. First frame is over here, second frame is over here, third frame is over here. But if you want to have another frame to the base, you can put it over here or over here. Base and the first frame you can have at the same point. The difference is that one of these frames is not moving because it's a wall coordinate frame, and the other one is moving because that is connected to the first link. And so as the link moves, that coordinate frame moves. Whereas the coordinate frame attached to the base is not moving because the base is not moving. Okay, but these two frames are located at the same point for simplicity or convenience, right? In modeling the manipulator. Okay, so this is the first joint, and this is where the first frame is located. The frame is attached to the link at this point. Second link, second frame, third link, third frame. Okay, as the link moves, the coordinate frame also moves with it. If you rotate the whole thing like that, all these 3 links will move like that, and there are coordinate frames to which they are attached to also move with the manipulator. Okay, so in this illustration, you can see 2 different sets of coordinates. One set is what is most familiar to you. If you look at this point here, you can say this is x direction, this is y direction, and then this angle is alpha, xy alpha. So xy and alpha tells you or describe your position and orientation. This is in a way like xy table. The difference is that xy table is usually horizontal, doesn't have to be, but physically people most cases see it like a horizontal platform, right? And this particular manipulator is in the vertical plane. It looks like, we don't know, right? Looks like it's in the vertical platform. Other than that, mathematically speaking, there's no difference, right? So xy and alpha, xy and alpha. So you can have a coordinate frame like that, x, y, and alpha, and you can figure out, give the value for x, give value for y, and value for alpha. You can have this point here. This point describes the operational point, okay, that the manipulator has assumed right now. And at the same time, if you go through the manipulator, you can see theta 1, theta 2, and theta 3. Right. So if you look at theta 1, you can control theta 1 independently of theta 2 and theta 3, because these are independent joints. And you can control theta 2, right, independent of theta 1 and theta 3. And same thing can be said about theta 3. So you can generate another coordinate frame orthogonal coordinate frame, theta 1, theta 2, and theta 3, like that. And you can measure the three angles, theta 1, theta 2, theta 3, and find out this point over here. Okay. There you describe the manipulator configuration. Manipulator configuration. Okay, you just spell out the three angles, just that. That is what is called the arm configuration. So you are referring to the same operational point in your XYZ coordinate frame, or rather XY alpha coordinate frame. And in the same time, you refer to the same point through your manipulator, referring the three joint angles. So when you deal with the angles, we say it's a joint space. This is the joint space. And when you deal with XY alpha, we call it operational space or task space. Right? You need to remember these names and understand it very clearly. So if you are an engineer, if you want to plan a maneuver using your manipulator, you would prefer to do it in XY alpha space, XY alpha. You want to move the endpoint along a certain XY alpha profile. Okay. And if you are the manipulator, you would not understand anything about XY alpha, but you will understand theta 1, theta 2, theta 3. All the motors and encoders, right? The servo system understand angles, theta 1, theta 2, theta 3, right? And the encoder readings, actuator signals. And if you look at the control paradigm, right? Control system, there we prefer to have angles, theta 1, theta 2, and theta 3. Okay. So when you operate a manipulator, you have to deal in both these spaces, joint space, Cartesian space. Okay. You plan your maneuvers in your Cartesian space, but when you want to control the manipulator, you have to transform them to joint space. Right. So you transform your coordinates from sometimes joint space to the Cartesian space, sometimes Cartesian space to joint space. So now let's look at how we can define the two coordinate frames in relation to each other. So there you can see the blue frame, X, Y, and Z of the blue frame over here. And then you can see another coordinate frame, the red frame, X, Y, Z over here. So that is the B frame. So the two frames are A and B, A frame and B frame. Frame B is located at this point. And if you know this vector, APBO, if you know this vector is the position vector of frame B with respect to frame A. So by specifying this vector, you specify the position of frame B, right? That is how you specify the position of an airplane with respect to an airport. Okay. So there are a lot of applications, right? You want to locate a point with respect to a coordinate frame. Now, the manipulator links are not just points. They have some sort of orientation. So you have to tell your orientation also. The orientation is also changing time to time, okay, continuously. So how differently B is oriented with respect to A. So that is the second thing you want to know, okay? If the two frames are on top of each other, then there's no orientation difference. They coincide, right? But in fact, they don't have to coincide. If they don't coincide, if there is a non-zero position vector like that. If you take this vector, and if it is non-zero vector, right? These 2 points do not fall on top of each other, right? There's a linear translation. But if you think about the orientation, right? It doesn't have to do anything with the position, usually. Position is one thing, orientation is another thing. When you talk about orientation, you can forget about the position and figure out how can I find a mathematical tool to describe the orientation of a coordinate frame with respect to another coordinate frame. So the answer is there might be different ways to do that, but people have agreed a long time ago, okay, let's stick to something like this. So what is that? This is how the world or scientific community agreed eventually to represent the orientation of a relative frame with respect to a reference frame. So if you read this one, let me help you. This trailing subscript, which is B over here, tells that the coordinate frame this vector belongs to. So when you say x hat B, y hat B, z hat B, what I'm essentially telling is that all these 3 vectors, they belong to frame B. They belong to frame B. Then you can see this leading superscript AAA. So the leading superscript is the coordinate frame to which it is related to. So this x hat, which belongs to B, is referred to A or related to A. This vector y hat B, which is a vector belongs to frame B, we refer it to frame A. So you have to write this vector with respect to another coordinate frame. Okay. And finally, this hat tells you, hat says unit vector. In this particular case, it's unit vector. But remember, in different disciplines, you use hat for different other meanings. Okay. If you look at the estimation and control, filtering, you figure out S hat as the estimate. Okay, estimate. So you read a sensor, but you are not very sure whether this is correct or not. Then you use a estimation filter, and filter generates the estimated sensor output. Okay, estimated state, and we call it hat again. So hat is used for other meanings also. In this context, this hat is basically the unit vector, right? So if you look at x hat B is the unit vector along x-axis of frame B. So that's what it is. X hat B, unit vector along x direction of frame B. And when you put A in front of that, you are telling you have to write this vector with respect to frame A. So it's very interesting. Now, let me ask you this question. If you have a coordinate frame like that, x, y, z, let's say B, what is the unit vector along x direction? It's a 3-dimensional coordinate frame. Every point around this coordinate frame has 3 coordinates, x coordinate, y, and z coordinate. So tell me, what is the unit vector along x direction? The unit vector along x direction of frame B.
XB hat?
It is a symbol. X hat B is the symbol for the unit vector of x-axis of frame B. Okay, this is the symbol for the unit vector along x-axis of frame B. What I'm asking is that, do you know that vector numerically? Can anybody tell me what is the unit vector along x-axis of any coordinate frame? In three-dimensional coordinate frame where you have three axes x, y, z, you have three unit vectors along x, y, z. What is the unit vector along x direction? So this is after studying 6 years at least about vectors. 2 years advanced level, 4 years undergrad. I'm asking probably the first vector question you have been asked in A level. What is the unit vector along x direction of a coordinate frame?
I.
What's that?
We denote it as I. Simple.
All these are what you are telling me is as symbols. Sometimes we give it I, J, K. Sometimes I is the symbol. That's a symbol. Here it is not IJK, it is X hat B, Y hat B, Z hat B. These are just symbols. I'm asking, what is it numerically?
Vector divided by its magnitude.
That is how you define a unit vector. You write the vector divided by the magnitude. That is the definition, how you define the unit vector. And you already gave me answers for the symbols. What are the different symbols that we use for unit vectors? Now you are giving me the definition. But this is not what I'm asking. Yeah, go ahead.
A physical quantity with one unit along and speed along the direction x.
Yeah, this is the definition of the unit vector. What I'm asking is, what is it numerically? You have to tell me the numbers. Numerically, what is the unit vector along x direction?
1, 0, 0.
1, 0, 0. I don't know why it took so long. Maybe I was not very clear, or you did not understand what I was asking. The unit vector along x direction is 1, 0, 0 for any coordinate frame. What is the unit vector along y direction then?
0, 1, 0.
0, 1, 0. And the unit vector along z direction is 0, 0, 1. Okay, right. So this x hat b, is nothing but 1, 0, 0. All right. But when you describe the orientation of this coordinate frame with respect to another coordinate frame, it's going to change. Because you have to take that 1, 0, 0 and write it with respect to coordinate frame A. So listen very carefully. There is a unit vector along x direction over here. It is 1 unit long from the origin along this axis. And with respect to this coordinate frame, we give it a name. Numerically, we described it as 1, 0, 0. Now you bring it over here. Now it's like this. You only see the magnitude the vector. So now you have to write it with respect to the coordinates of frame A. Is not anymore 1, 0, 0, okay? Because here, with respect to frame A, 1, 0, 0 is somewhere here along x direction unit vector. 1, 0, 0 is this point of frame A, and 1, 0, 0 is somewhere over here in frame 2. So you bring this unit vector and place it over here without changing the direction. That point is not going to be 1, 0, 0 anymore, but you have to write it. You have to figure it out. You have to calculate it. Then the 1, 0, 0 becomes another 3 numbers. Okay, but still a unit vector because the magnitude, length is 1, because length is 1, still a unit vector, but it's not going to be 1, 0, 0. Do you understand that point? Yes or no? If you do not understand, I can explain, no problem. So you take 1, 0, 0 over here and bring it over here and then find out what is the x coordinate, y coordinate, and z coordinate now, right? You write these 3 coordinates over here, and that is what is called A x hat b. Do you understand that point? If you do not understand, please tell me no. That's okay.
Sir, can you explain it again, sir?
Right. So let me use the pen. Oh, that's the pointer. Right. So there's a unit vector here, right? So which is 1, 0, 0, right? I write the column vector 1, 0, 0. So this is x hat b, right? X hat b. Now I bring this one from here to here and place it like that. So this is the same vector. This is the same vector, right? So now this length is 1, right? Length is 1. It's a unit vector, right? So this has these coordinates now, right? So like that, 3 coordinates. So what is this coordinate here? What is this coordinate? What is this coordinate? So you get 3 different coordinates now, right? For the same vector, right? This is 90 degrees over here, right? So there's a dotted line here, right? So this quantity, let's say this is A, this is B, this is C, right? When you get this ABC, right? A, B, C, put as a vector, and this is what is called this one, AX hat B. Do you understand that?
Yes, sir.
So does everybody understand that point? All the others?
Yes, sir.
Right. Yeah, fine. So this is the technique. after x hat b, you have to do the same thing for y hat b, right? Somewhere over here, right? Y hat b. So let's say this is 1, 0, 1, 1, 0, 1, 1, right? 0, 1, 1 as a transpose, right? It's actually a column vector. When I write it as a row vector, I put the transpose. Okay. So this whole vector, I should have taken from here to here the whole length. Okay, but doesn't matter. So you have to take one by one. First unit vector, second one, third one, x, y, z, right? Bring it over here to the frame A and place it at the origin and calculate the 3 coordinates. So then this becomes a 3 by 3 matrix. Okay, 3 by 3 matrix. So this matrix is the orientation matrix. Orientation of frame B with respect to frame A. Right? So this is the orientation matrix, 3 by 3 matrix of frame B with respect to frame A. So if you have the orientation matrix, now you know how to read it. If you look at the first column, second column, third column, right? So let's say this is a orientation matrix given to you, right? So it has, it is like this, 3 by 3. So there you have the first column, right? Over here, the first column is the unit vector of the relative frame, that is frame B, x-axis, right? Written with respect to the coordinates of frame A. Okay, it is not anymore 1, 0, 0. All right. And then the second column, what you see is the unit vector along y direction of frame B, that is y hat B, which is actually 0, 1. This is 0, 1, 0. Okay, so let's make that correction. So 0, 1, 0. Okay, right. So it is not anymore 0, 1, 0 when you bring it to the to frame A, and then because it doesn't fall on y-axis, it is in some arbitrary direction. You have to find out the shadows, right? Shadows on x-axis, y-axis, and z-axis. All right. So these shadows are the components along x, y, and z of frame A, and you write the 3 coordinates over here. And you go on and do the same process for z-axis. You have the 3 by 3 matrix, and we call it orientation matrix. Is that clear? Right. Can you move on?
Yes.
Right. So I want you to write with me, right? Why don't you sketch this on your paper? Get a piece of paper, draw a frame A, right, and frame B, right? And there's a vector attached to frame B, right? This is frame B, and this is a vector attached to frame B, and I call it BP, right? BP. So BP has 3 coordinates: BPX, BPY, BPZ. Right? Nothing new to you. And then, of course, you can see the origin of frame B, right? Is over here, and that point is is given a name APBO. Right? APBO, which means this is the origin of B. Right? When I say PBO, I refer to the origin of frame B, but in front of that I have A, which means I have written this point with respect to frame A. Okay. Always every vector that you write, there's a reference frame. You have to write this reference frame in front of the vector. Okay. But here we are not really bothered about this orientation of the position vector APBO. This is just for completion, right? We are actually concerned about the orientation, right? So let's take BP. BP has 3 coordinates, BPX, BPY, BPZ, like that. And now I take this BP from here to here, right? And I'm going to change the leading superscript B to A. I'm going to write AP. I'm going to write AP. And for the moment, let's disregard APBO, okay? So imagine a vector BP, BPX, BPY, BPZ, transpose described in B, right? Okay. Translate it to frame A origin and disregard translation APBO and determine the vector with respect to A. So this is what we are supposed to do. So how can we do that? So you can see this B, frame B, I have taken it over here, translated through the unit vector over here. Now the 2 coordinate frames are on top of each having the same origin, but they are disoriented. Okay, so B is disoriented from A. Okay, so A is the reference frame, B is the relative frame, B is oriented in an arbitrary direction. So we want to describe the orientation of frame B. So for that we have to do this process. So this becomes a bit complicated on screen, but if you go slow, step by step, you will see it is very simple, right? So anybody would write the same thing. So what I want to find out is what is the total components on the x-axis of A. X-axis of A. Now, if I pedal back here, I know that there are 3 vectors: BPX, BPY, BPZ, right? BPX is the x coordinate, BPY is the y coordinate, BPZ is the z coordinate. There are 3 coordinates along x, y, and z. So all of these 3 vectors, these are component vectors, right? They're generating some x component on the frame A. Frame A, there's the x direction. So all of these 3 guys, these components, create small x component over here. And they also create small y components over here. And they all create small z components over here. So if I want to write this BP, and if I want to write AP, I want to find out what is the x coordinate, y coordinate, and z coordinate. Simple, right? So if you want to write a vector with respect to a certain coordinate frame, what you need to do is to find out what is the x coordinate, y coordinate, z coordinate. Just that. So what is the x coordinate here? So I want to find that out, right? What is the x coordinate? That is px with respect to A. So what is that? So this is what I want to find out. So there are 3 components over here. this guy, BPX, is creating a small contribution over here. BPY creates a small contribution over here. BPZ makes a small contribution over here. All three coordinates contribute to APX. So I want to find out what are these contributions. So to do that, I need to calculate the shadow of BPX, right, on the x-axis over here. Shadow is the cross product. You know that, right? When you stand upright, your shadow falls on the ground. And let's say that direction is x-axis. How long is your shadow? And that is the contribution, your contribution along x-axis. Okay, and then you have y-axis, z-axis, other two components. They also create shadows. You have to calculate those shadows also. That is the whole thing, the net contribution, right, on the x-axis over here. And that is what is called APX. Right, so let's take the first component, BPX. If I want to calculate BPX contribution, right, on x-axis here, I have to get the BPX, right, and that is the magnitude. It is this long, BPX. This is just the magnitude. But after that, I have to calculate the shadow. Shadow means the cross product between these two axes. This is the x-axis over here. This is the x-axis over here. So I need to get the dot product. So that is x hat b dot x hat a. Okay, so this is the contribution. So this is the contribution by BPX on x hat a. Just this component, BPX. So next page, this is the first part, right? BPX, x hat b, x hat a. So this small quantity is the contribution by BPX on x hat a. BPX on x hat a. X hat a. Is that clear to you? So then we do the same process with BPY. This time BPY is the component of BP along YB, this direction. You bring that one over here, and then you calculate the shadow on the x-axis. So when you do that, BPY, right? You have to add to this one. Have to add to this one plus, right? This time it is BPY, so I write it like this. BPY. Then you have to do the direction, right? So direction is y hat b, the vector is in that direction, dot x hat a, because you are calculating the component on the x axis of a, x hat a. So the next slide, the second term is this BPY, y hat b, x hat a. Then the third component is the z component of the vector BPZ, and that one is along ZB axis. ZB axis. Now you have to calculate the shadow which is falling on the XA. x direction of A, right? So get the dot product. So all three components, BPX, BPY, BPZ, they create three shadows on the same axis, which is x hat A. So when you add them together, you get the total contribution by this vector BP, right? By this vector BP along the XA axis. And that is the X component of the vector when you have it in the frame A. So please write it down. Write it down yourself. Draw this sketch. Otherwise, this will be very, very tough for you. You won't do it right now. Draw the two coordinate frames and then write down the first line over here. Then you take the second component, second axis, that is YA. So this vector, these three components will create three shadows on YA, this time YA. Okay, so you have to get the dot product with respect to YA. So you can see it over here, YA, YA, YA. Same component, right? BPX, X hat B. But the shadow you calculate, the component is along YA. So therefore you get the dot YA, dot YA, dot YA. And after that you take the Z component, that is along the Z axis of frame A, but you get the same three components, BPX, X hat B, BPY, Y hat B, BPZ, Z hat B. These are the three components, right? Now you get the dot product with respect to ZA, ZA, ZA. Right? So you can see the process here very clearly. You can see this is the same component, right? Three components. See, BPX, X hat B, BPX, X hat B, BPX, X hat B. But the same component, which is over here, right? The same component creates three shadows on X, Y, and Z axis of frame A. And then you get the other three components, right? You can say this one, BPY, 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 and BPY also generates three shadows along X, Y, and Z. BPZ here, right, which is along Z axis of frame B. Now it's not along Z axis of frame A, right? It's in arbitrary direction, but it creates three shadows on XA, YA, and Z. Right? You need to understand details of this process. It's very simple, but you need to take some time to understand what these equations mean, right? You need to see the physics, not the mathematics, okay? Mathematics can be very intimidating if you do not know the physics behind it. If you know the physics, what is happening, any complicated mathematics is actually not complicated, okay? So every time you say this is very tough mathematics, the reason is you do not know the physics, what is going in the real world. So now you can rearrange this expression, right? Because you can see this is XA, 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 YA, 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 ZA, 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 right? So there are many patterns over here, and also BPX, 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 right? In this simultaneous set of equations, right? You can see bpx consistency here, bpy here, bpz here. So you can take that out. First element here, right? You can, in all three equations, you can write it bpx here. Second element in these three equations, bpy, you can put it over here. This has to be bpy, right? Sorry about that. Maybe I can do it a little later. Well, I will edit it later. Before I upload the video and slides, I will edit it. This is bpx, bpy, bpz. Okay, you know that. Now, this is really beautiful. Now, you see on the left-hand side, you have apx, apy, apz. What is that? This is the vector referred to A. Okay. This is the same vector, bpx, bpy, bpz, right? Referred to frame B. Now, you have the relationship between two frames. The only difference between these two descriptions is the orientation of frame B, right? So there are two frames which are not in the same orientation. That is the only difference, right? This translation also we have neglected, we have removed it. Now, both of these frames are having the same origin, but different orientations. However, now you have written one vector which belongs to frame B, right? Now you have written it with respect to frame A. And this is the result you have got. See how beautiful it is, right? And there you can see again, first column, second column, and third column. What are they? This is x hat b dot x hat a, y x hat b dot y hat a, x hat b dot z hat a. So again, if you see this dot product, right? You know that you can change the order around the dot, right? Even though if you say x hat b dot x hat a, or if you say x hat a dot x hat b, you change the position. It's not gonna. It's okay, right? It's correct, still correct. So and if you read this one, I don't know whether you can read it clearly, right? The physical meaning of a vector like this. The physical meaning of this column vector is actually you have written this content, right, with respect to A. Can you see that? X hat B, X hat B, X hat B is the same content, but first you refer it to A, then to, refer it to XA, then to YA, then to ZA. Same vector referred to 3 different coordinate axes of frame A. So how do you mathematically explain that process? Is like this. You write X hat B with respect to A. So physically, this is what you're doing, right? Mathematically, it is kind of complicated, it looks like, but physically, it's a simple operation, right? What is that? You write X hat B, which is the X coordinate, right, of the vector which belongs to B, right? Now you're writing it with respect to A, frame A. And if you look at the second column, you can see the same thing. You can see Y hat B this time. You are writing it with respect to the major axis of A, X hat A, Y hat A, Z hat A. Okay. So vector Y hat B written with respect to A. And the third column Z hat B written with respect to frame A. Right, fine. So then we give it a symbol ABR. ABR means the rotation matrix of B with respect to A. So leading superscript is the reference frame, leading subscript, which is B over here, is the relative frame. Any questions, please? Any questions, please? This is one very important thing today, one very fundamental thing in robotics, right? If you do not understand this, life will be very difficult, right, in the context of this module. So therefore, you have to get it, grip it firmly today, right now. Set of vectors belong to a certain coordinate frame, are being written with respect to another coordinate frame, and this is the process. And it's a unique process. There are no other ways to do that, right? And it's a very simple, or also you can physically figure it out what's happening. So now when you see the rotation matrix ABR, right, when I give you a rotation matrix, you need to be able to understand what it is, right? What is the meaning of this matrix, 3 by 3 matrix? It has the first column, second column, third column. What is first column? First column is the X coordinate with respect to the 3 axes of the reference frame. What is the second column? Second column is the Y coordinate, right, of the vector written with respect to the 3 axes of the reference frame, like that. Okay, right. Now, what we are going to do here is that if you see this one, X hat B, Y hat B, Z hat B, right? So I have written very much the same thing, ABR, right? But now you know I can do a simple operation over here, if you don't mind, right? If I change these two together, why don't you do that on your piece of paper, right? You interchange these two quantities, because around the dot operator you can swap the two quantities, right? So now you write x hat a on this side, and then x hat b after that, after the dot. Why don't do that? Please do it. Before the dot x hat a, and after the dot x hat b. Change everything. So when you do that, you get a very interesting phenomena, right? You will get the first row, right? What is the first row? First row is x hat a here, x hat a here, x hat a here, and written with respect to x hat b, y hat b, z hat b. The exact opposite, right, of what we just discussed. Now it is x hat a written with respect to coordinate frame b. So we have changed or swapped the reference and relative frames. Now b is the reference, it looks like, and a is the relative. Okay, so the first row is actually b x hat a, x hat a written with respect to frame b. And then if you look at the second row, it will be ya before the dot, ya before the dot, ya before the dot, and after the dot x hat b, y hat b, z hat b. So it looks to me like ya being written with respect to the coordinate frame b. So it is y hat a written with respect to frame b. And it's a row vector. Because it's a row vector, I have to always write down the transpose, because generally we write vectors as columns. Third row is also, you can see, when you swap the two quantities around the dot, it will be frame b, the reference, and a relative. And you are writing z quantity of frame a with respect to. So when you have these three row vectors, right, the matrix we write is BAR transpose, because it's a transpose, BAR transpose. So they are the same. ABR is equal to BAR transpose. So BAR, what is BAR? BAR so BAR is equal to ABR inverse. You know that, right? When you change your reference and relative frames, your transpose matrix, your rotation matrix is going to be the inverse. Okay, you know that. So with this relationship, we have just found out, which is ABR is equal to BAR transpose. So BAR is ABR inverse. So if you have the inverse transpose, you get the matrix. You get the matrix. So therefore, we write it like this: ABR inverse is equal to BAR, which is equal to ABR transpose. Okay. So you don't have to get the inverse of a rotation matrix. Simply you can get the transpose for that, right? Why? Calculation, the inverse calculation of a matrix is computation intensive, and even if you do not do it manually, even if you use MATLAB to do the matrix inverse, we recommend to avoid inverse calculation as much as possible. So even if you do a MATLAB code, don't think that okay, it is okay to have inverse. If you want really fast computation, you can replace rotation matrix inverse with rotation matrix transpose. Okay, transpose is easy and a faster operation. Any questions so far? Right. So if there are no questions, we're gonna take a little break now. So about 10 minutes, right? So I'll see you after the break.